So we're gonna have a slightly delayed start. Thanks for bearing with us, people. Our speaker today is Sam Grunblatt. He is a research scientist at Johns Hopkins University. Previously, he was at American Museum of Natural History, and he did his PhD work at Hawaii. He's interested in, as you can see, big planets around big stars, but also, planets and star demographics kind of writ large. So I'll let Sam take it away because we've started a little late on this. But you're all missing out on the in-person audio visuals, which are pretty great.
All right. Make sure that we don't have any echoes. Seems like probably if people can't hear me, just let me know. I'll leave it to you to monitor the chat because I can't look at that many things at once. But okay, I think if I do this, then maybe if I minimize this, okay. Does that work? All right, I think that should work for everyone. Okay, great. Great. Hi, thanks to all of you for coming. And Praval, thanks for that great introduction. I guess I'm blocking the projector a little bit. Yeah, so since we're already a little bit late, I'm just gonna jump right into things. Okay, so there we go. All right, so yeah, so just to sort of set the scene really quickly, basically the evolution of star and exoplanet systems in 30 seconds. Basically, you start out with a protostar that's surrounded by a disk of like dust and gas. Over time, that protostar will evolve into a main sequence star. That dust and gas might evolve into planets around that main sequence star, and then basically they'll stay like that for a few gigayears. Then at sort of the end of the star's life, the star will become more evolved. It'll get larger. It'll become a red giant. And that can affect the planet population around it. And then eventually the star will evolve into a red supergiant, the planets will get engulfed, and you'll be left behind with some sort of white dwarf system. So for this talk, I'm going to be focusing on the evolved stage of planetary evolution. I'm going to be talking about systems that are sort of, sun-like, so masses of like 0.8 to 2 solar masses. And so basically, just focusing on those systems for this talk. And these systems are interesting because we have a lot of planets that we know of now around main sequence stars, thanks to missions that a lot of people in this room have helped with, like Kepler and K2. But we don't have that many systems around evolved stars. And that's largely by design. These missions basically weren't designed to be targeting these red giant stars. And so if we want to basically understand the planet population of these stars, we have to basically we have to specifically target them a bit more and actually, study their demographics in a more focused way instead of just having them be like the sort of add-on of, Kepler stars that weren't what we thought they were and things like that. And so actually a decade ago, there was no evidence for transiting planets around evolved stars. And so for a long time, people just thought that around giant stars, basically as the star grew larger, if there were planets that were in sort of, less than 1 AU orbits, they would all basically in-spiral right away. But we now know that that is not the case. So thanks to Kepler and K2, we did find serendipitously like a handful of planets around red giant stars. And so this is basically what we knew of at the start of 2018. We kind of had a handful of transiting exoplanets around evolved stars that we had found, and they tended to be on these short period orbits, so they weren't in-spiraling quite as fast as we had thought. And so that's great. So we knew that they were there. We should go look for more of them. And so then later in 2018, TESS came online. I don't think I have to explain this to anyone in this room, but TESS was really great at finding planets around giant stars because it was an all-sky survey. And so because of Malmquist bias, basically we see more bright stars because they're bright. We had a lot more red giant targets that we could get to in this survey. And so TESS has been really awesome for finding planets around red giant stars. And so, so already TESS has basically in the first 5 years doubled or more than doubled the number of planets that we know of around these red giants. And it will definitely at least triple that number if I can get my act together and publish all of the faint red dots or faint red stars on this plot. And so basically, again, the gray stars are basically the same green stars that I showed on that other plot. There were planets before TESS. And now, since TESS has been launched, we've already published a handful of these populations in all of these publications that are listed there. And we have a bunch more that we now have, basically we know that they're planets, and we just need to get a little bit more data to confirm them and get them out the door. And the reason this is that we've been able to find all of these planets is largely due to the GIANTS pipeline. So this is a pipeline that was developed by Nick Saunders, who's a PhD student at the University of Hawaii, and also was I don't know exactly what his title was, but he worked at NASA for a little while. And so he knows a lot about basically designing light curves and things like that. And thanks to the work that we did together, basically we were able to target hundreds of thousands of red giant stars and then produce these sorts of summary plots for all of them, where we could actually see, okay, is there a transit in these light curves? We can run a VLS on the data. We can look for oscillations in the power spectrum to see if the stars are oscillating as well. And so this has been a really useful tool for identifying these planets around red giants. But one of the most important reasons for building this tool was that other pipelines that were developed for TESS were not finding these planets. In fact, because the transit durations are generally over 6 hours long, a lot of the sort of default pipelines that search through the TESS data basically would smooth over these transits completely. Because they're usually looking for much shorter transit durations, they would just remove the entire transit, treat it as noise. And so we'd end up with, the sort of line you're getting on the bottom in red there, versus our pipeline where we're basically not doing a sort of like, removing noise on a certain time scale, but rather using a more principal components analysis approach to detrending the light curves. We're able to preserve these longer transit durations. And the other thing is that by using this principal components approach, we can also find really low SNR transits without actually diluting them. So again, this is a comparison between our GIANTS pipeline and 3 other pipelines. And basically what you can see is that our pipeline, which is shown by the red dots here, does a good job of preserving those transits while also having the lowest CDPP scatter of any of the light curves that's shown here. So yeah, it's been really great for actually finding these planets, and that's why we found so many within our own search, as opposed to some of the other teams that have sort of found these things serendipitously. Okay, so that's great. Planets around evolved stars, we're going to have a lot more of them. Cool. But why? Why should we actually care about these particular systems? And today I want to break it into sort of 3 different things that I'm interested in researching, and sort of we'll walk through each larger category throughout the rest of this talk. So first, I wanted to talk about planet reinflation. Okay, so just for a little bit of background, so planet inflation is something that we've known about for a long time. We've seen a lot of planets that are basically larger than we'd expect from a sort of like, basic model of what the planetary structure should be. This is why, for example, like brown dwarfs can often be smaller than like hot Jupiters, is because those hot Jupiters are inflated. And so there are a lot of mechanisms that can cause this inflation, but some of they all operate differently. But if you look at planets around evolved stars, you can actually start to test between some of these different mechanisms. And so just generally, here I've broken into 2 large classes of mechanisms, where class 1 are the sort of mechanisms where planets basically are, the interior of the planet is heated directly from the stellar radiation. Basically, the star irradiates the planet's surface, and then the heat moves into the interior of the planet through motion in the planetary atmosphere. Whereas in class 2 models, basically, or class 2 mechanisms, the planets can hold on to their heat from their initial formation, but basically they're not having heat from the star then deposited into their interior. They merely have delayed cooling after their formation, so they can't get basically larger at late times. They can only get smaller. And so if you want to distinguish between these 2 classes, basically what you can do is look for systems that have evolved from sort of main sequence to post main sequence systems. Because if class 1 inflation mechanisms are correct, then basically planets can re-inflate at late times, whereas these class 2 mechanisms are correct, then you don't see any re-inflation, basically. And so here's just an example of a planet radius versus age, or K297b, which is a planet around an evolved star, or a hot Jupiter around an evolved star, where we basically tried to figure out whether this planet has been re-inflated or not. And so the different lines on this plot, all of the colored lines correspond to different reinflation models with different heating efficiencies, whereas the black line below them is the basically a delayed cooling model where there isn't any additional heating that's allowed in the planet. And if we compare basically this planet to a very similar planet that's a similar mass, similar orbital period, around a similar mass star that just happens to be on the main sequence, what you see is that the main sequence system looks to be smaller. And so it's easier to basically explain at least this particular example if you allow for reinflation in this particular case. And we've actually now seen this in a handful of cases. So back in 2017, I found a second case of this where basically, again, reinflation seems to be the dominant mechanism for what's going on. And what's interesting is then if you compare both of those planets to basically a whole bunch of sort of similar main sequence systems, and then try to fit them all with delayed cooling models, you basically need a different delayed cooling model for every single planet. Whereas reinflation, you don't need as many models. And so the evidence seems to be continuing to point toward reinflation in these systems. And yeah, and that has continued. So actually, these are a couple of models that were made by Daniel Thorngren for a couple of new test systems that we're working on right now. And basically what we find is if we fit for this reinflation, we can get a heating efficiency for these planets, and we get a heating efficiency that agrees perfectly with what we found from those original K2 systems. So evidence keeps pointing toward reinflation. I think we're getting to the point where people can stop saying that it's not happening. But the question is, how ubiquitous is this reinflation? Do all hot planets with atmospheres reinflate? So basically, we know that all of the planets that are in the orange zone here are basically unambiguously inflated. They're past this boundary of like what you'd expect for a ball of pure hydrogen and helium that was experiencing a certain incident flux. But below that line, it's much harder to tell. The rate of the inflation is going to be degenerate with the composition of the planet. And so, you could imagine that you have a planet that has been reinflated, but because it's still, only one Jupiter radius or something like that, we couldn't actually tell whether that planet had experienced inflation or not. But we can actually try to start investigating this. So this is just showing another one of the systems that we recently found. And one of the things that I think is really cool about this system is that we could basically only find it using our pipeline. And so this is comparing, basically different phase folded light curves for 3 different pipelines versus our own, and then the BLS equivalent of that. And you can see that the signal pops out pretty clearly in our BLS, but not in the other 3 signals. And since I made this plot bit or this figure, we also got some Spock data of this particular target, and we also see the transit there. So we're pretty convinced it does exist. We've also gotten RVs, so we know that this is a real planet. So this is really exciting because this is sort of like the smallest or the lowest mass planet that we've ever found around an evolved star. And as you note, it's like 7.3 Earth radii, but only like 20 Earth masses. So this is a really, really low density planet. I think it has a density of like 0.4 grams per centimeter cubed or something like that. So it's like on par with Saturn. And to just sort of put it in context, why this is so exciting. So this is just showing basically the population of planets from the NASA exoplanet archive. You can see where I basically highlighted these sort of like hot Neptune systems. And you can see that basically all of the hot Neptune systems that we knew of before then are kind of on the lower right of this plot. So they're all basically around main sequence systems or systems that are basically, still very close to the main sequence. Whereas this is the host star here is like 3 solar radii. It's like a bona fide red giant star. And so this is the first hot Neptune that we've ever found around a red giant star. And it's so for that reason, it's pretty exciting. And the host star itself doesn't seem to be particularly weird or anything like that. So to just put this planet in context, it's low mass, it's low density, it has very high irradiation. It's on an orbital period of like 4.2 days. And so the irradiation on this planet is over 1,000 times the flux on Earth. And so this all implies that there should be a lot of atmospheric mass loss in the system. Very low density, higher radiation means that you should have a lot of stripping of the planet's atmosphere. And so we can actually calculate this. And so, you can use this m dot equation to basically work out what you think the rate of mass loss should be. If you also know basically the XUV flux on the planet. And that we can get by basically comparing to other models of what people think the XUV flux over the lifetime of a star should be. And so basically that's what we've used here is we've now integrated what we think the XUV flux should be over the lifetime of the planet for this particular star. And by doing that, basically, we can work out how much mass loss we would expect the planet to experience over its entire lifetime. Yes, Paul?
So Sam, quick question on a lot of this, you have I'm guessing you have good lower bounds on ages because of where your stars evolve to.
Yeah, so I mean, basically, for a lot of we know that all of these stars are old, right? Because they're evolved. It is really dependent on how well of a mass measurement we can get for the star, which for red giants, generally we can do pretty well because a lot of times we can get an astroseismic signal and use that to determine what the mass and the radius is to pretty good precision, usually better than 10%. For this particular system, we couldn't detect an astroseismic signal, so we're just working with basically the Gaia radius as well as some other sort of parameters, but I think we still got a mass to we have like high resolution spectra and things like that we got the mass to, I think, within 15%.
Do you do any like twin studies about like where in reinflation some of these might be based on the astrocyte model?
Yeah. I mean, I think that's definitely so the plot that I showed before where I had like the different planets where I was trying to compare that was sort of the idea there, to try and compare these similar systems to say, how do they look different? And the bottom line is it looks like the younger systems tend to be smaller planets. So I think that's, trying to show evidence that this reinflation exists. We could now do this for hot Neptune systems with this particular system, but I haven't actually done that yet. Yes. So this particular system is definitely a single star system. In general, we're not trying to remove stars based on binarity from our survey, but because we've been getting RVs, if there is a second star in the system, we can usually either see it with the imaging or we detect it via RVs. And so for this system, we didn't see either of those cases. And I think for all of the systems I'll be talking about today, that's the case. Okay, so yes. Yeah.
I don't study hot large planets around any kind of star. Is it calling it a hot Neptune based on its mass?
Yes.
Or its radius?
I would say on its mass, basically. Like some people would probably call this a hot Saturn based on the fact that its radius is 7 Earth radii.
I'm just trying to see where these fit into there's other work out there looking at planets in the hot Neptune desert and things like that.
Exactly.
And they're typically calling it a Neptune based on size.
Okay.
And here, I mean, I think the mass is a very way to characterize it because then where it may have started and where it may have gone.
Right.
In terms of things
Yeah.
trying to make sure I have that.
Yeah, I don't know if there are a lot of other sort of hot Saturn. I don't know if there are a lot of planets that are 7 Earth radii around at on 4-day orbits around other stars.
I don't think the population is large.
Yeah. So
Right.
I don't know whether it's better to call it a hot Neptune or a hot Saturn, but I went with hot Neptune because of the mass, basically.
That's clear. Okay.
Yeah. So basically what I'm showing here is just for every planet on the NASA exoplanet archive where I could calculate this mass loss rate and then basically try and figure out what the total fractional mass loss was by combining the mass loss and then basically multiplying that by the age of the system divided by the total planet mass to say, okay, what fraction of the total planet mass has been lost in this system? And so if we do that, basically, you can see that, basically everything is kind of, on the left side of this plot, more or less all of the systems have lost less than 0.4% or have lost less than 40% of their mass to atmospheric mass loss. And the only things that have much higher than that are these sort of hot rock systems where basically they can lose all of their atmosphere and it won't change their size very much. And so here I'm just adding a line of what we expect sort of the atmospheric mass fraction to be for all of these different systems, where basically systems above that line have atmospheres and systems below this line have atmospheres. And you guys might know what's coming next, but if you add this planet to this figure, you see that it falls in the no atmosphere regime. And so basically this planet has lost so much, or is predicted to have lost so much of its mass over time that it basically shouldn't have an atmosphere anymore. The planet should have lost around 2/3 of its mass, even though only about 1/3 of its mass should be in its atmosphere. So I don't know how it still has an atmosphere, but I have some ideas, and I think they might be related to reinflation. So basically, if you want to save this planet's atmosphere, this is again just a plot of radius versus age, where we have where we've plotted just a fiducial sort of mass loss model and a reinflation model that both intersect with the current radius and age of the system, which is shown by the green dot here. And Basically, if you compare these two models, they don't make a huge change in the radius. So basically at 1 gig-year, the difference in radius is only about 16%. But because the XUV flux is strongest at about 1 gig-year, and it depends on the density of the planet, a change in 16% in radius corresponds to almost a 50% change in the mass loss rate. And so essentially, if we allow for reinflation in these hot Neptune systems, we can reduce the expected mass loss by a factor of 2. And we can actually hope to, so that seems like it would save the planet. And I mean, still makes it difficult because then you're only losing one mass of atmosphere, or like, you know, the 30% of the planet's mass, which should be the entire mass of the atmosphere, but it does a better job of saving the planet's atmosphere. And we can actually hope to try and reobserve this with James Webb. And so the way to do this would be to try and look for like outflows, things like metastable helium. And so with space-based telescopes like HST or JWST, you can actually look to detect this metastable helium and see whether the planet is actively losing mass right now. And basically that should tell you whether the planet's reinflated or not. If the planet is actively losing a lot of mass right now, that means that probably has started recently, because it couldn't have been losing that much mass over its entire lifetime. And so it's probably is actually reinflated recently. Whereas if we don't detect it, that means that it probably was able to survive for other reasons. Maybe the star was just very inactive, doesn't have a big XUV flux, and the planet was able to just hang out with its very low density. And so while we're talking about observing we can do with the space-based instruments, I just wanted to shift gears to another sort of post-main sequence system where we can hope to investigate reinflation, and that's KELT 11. And so basically, this system is again a really puffy like gas giant planet. Yeah, I guess I don't have it here, but basically you can see where it lies on this spot. This is an actual hot Jupiter, but it has a mass of like less than 100 Earth masses. So again, very low density, and so it has a really high scale height, and we can start to look into it with James Webb and see some pretty big features. And basically, we can simulate what we'd expect to see for KELT 11 based on some earlier Hubble observations. I think were taken by Nicole. And what was really one of the things that's interesting about the system is that like the sort of water feature that was observed, which is shown by the green on this figure, you can see that there's like a weird bump to it. And basically that bump is really hard to explain unless you invoke like disequilibrium chemistry. And so basically that's what we've tried to do here is if you allow for disequilibrium chemistry, then we can get the red, which is hydrogen cyanide, HCN, to basically explain that bump. Or, you know, maybe it's something like there's just a lot of noise, or the cloud deck is really high in the system or something like that. But basically, you know, however we can like if this bump is real, that would explain, that would, the reason for that could be due to like strong vertical mixing in the planet's atmosphere. And that would be a sign of reinflation, because if you have strong vertical mixing, then things that are on the surface are getting deposited into the planet's interior, like the heat. And so, you know, if we do see signs of this disequilibrium chemistry, that would be a sign of strong vertical mixing. But also, if we just see clouds, so if we just see a flat line, that also would be a sign of this strong vertical mixing. And so basically, even if we get a very boring detection for this particular planet from James Webb, it's still a pretty exciting result in terms of understanding planet and reinflation. And so we put in this James Webb Cycle 2 proposal, and we'll find out how that went hopefully in a month or so.
So what's your way to falsify this? Clouds or those things that produce that? Like, what is your way to say this isn't stronger?
So basically, if all we see is like these other features, like the CO2 feature, the water feature, and things like that, and we don't see any signs for disequilibrium or something like that, that would be evidence that the mixing isn't that strong. And that could also go along with some of these tracers of atmospheric mass loss as well, because those don't require strong vertical mixing either. And so if we're only seeing atmospheric mass loss, which I think has been detected in this particular system, then you won't see strong clouds. You won't see this disequilibrium chemistry. Basically, you should just see water and CO2. Cool. All right. Well, that's pretty much all I had to say about planet reinflation. Does anyone else have any other questions about that?
Can you go back to that plot with the reinflation and the release, the orange and blue one?
Okay.
What little bump on the right from the reinflation?
Yeah, something in subgiant evolution, I'm pretty sure. So basically, like when stars, depending on what the mass of the star is, and I think this star is around like 1.3 solar masses, a little more massive. Basically, the like initial evolution from the main sequence off onto the subgiant branch, there's like a little kink, I think, in that motion, and so basically the evolution in temperature or like irradiation basically is not even throughout that process, and so that's what's causing this bump basically.
We thought about towards the end of the red giant evolution, and then like I guess it depends on the mass of the star. What how your reinflation kind of starts to tick down, as you have the star evolving at the same time as the planet, what that might look like.
So I mean, basically, as the star evolves up the red giant branch, it's just going to get larger and larger, and so the irradiation will just get higher and higher on the planet until the planet is inside the star.
Yeah.
And so that's what I'm actually going to talk about a little bit right now. Yes. Uh-huh.
What's the time scale between the planet and the star?
That's a really good question. So people are researching this right now. The idea is that reinflation is a pretty rapid process. So it's kind of on like the tens of millions of years or something like that. And that the stellar evolution is also around that sort of like tens to hundreds of millions of years. So I think reinflation, the current belief is that basically with respect to the stellar evolution, the inflation is like instant. That basically the planet instantly responds to whatever changes the star has done. But that only has come out in the last couple of years. Mm-hmm. All right. So moving on. So the second thing that these systems really interesting are for is orbital dynamics. There's a lot more that we can understand about star-planet and planet-planet interactions in these evolved systems that you can't get at with main sequence systems. And so one of the things that you can look at is the obliquity of a star relative to its planet's orbits. So basically, people have known that in multi-planet systems, planets that are initially on aligned orbits can actually torque one another and then end up becoming misaligned with the host star. But in post-main sequence systems, it's possible that it goes the other way, that basically in a star that starts out being really hot, and so it only has a radiative envelope at first. Eventually, as it cools off, it'll start forming convection in that outer layer. And that convection then can basically cause the obliquity of the planets to damp and realign with their host star. And so this is something that we've started looking into. Basically, the main thing here is the red vertical line, where to the right of that line, all of the planetary systems, or the vast majority, seem to be well aligned, whereas to the left of that line, the obliquities are kind of all over the place. And so now we want to look at the systems that are that used to be on the left side of the line, now they're on the right side of the line. So those are the red stars that we've targeted here. And what we found, we tried to get measurements of 3 of them. We were successful twice, and we found that both of those systems were also well aligned. And so it does seem that the convective envelope of the star does have something to do with aligning the planet's orbits with the spin orbit, stellar spin. There we go. The other thing is that we've noticed that close-in planets around evolved stars seem to prefer eccentric orbits. So if you look at everything that's kind of at 30 days or less on this plot, where basically the filled in, the red points are the evolved systems, the black points are the main sequence systems, and filled in things are transiting, open symbols are not transiting. We find that for these shorter period things, the eccentricities of the evolved systems is significantly higher than it is for these main sequence systems at like a 1.5 sigma. So it's significant, but it's not super significant. But that's something that we found back in 2018 when I was working on my PhD. And so we've continued to look at this with the new test systems, and they fall. Oh, yes. And so we can use this to determine like the in spiral versus the circularization timescale for these systems, because basically hot Jupiter formation should depend on those 2 timescales basically. And what we find is for main sequence systems, those timescales are pretty comparable. And so we think these systems are basically in spiraling and circularizing at sort of the same time. And so you result in kind of like a focusing of the planets on this plot that you don't see for the main sequence systems. And yes, and so when we added the test systems, you can see they basically fall exactly where we'd expect, more or less right, right in line with all of the other evolved systems that we found so far. Yes. So basically the idea is that that we see some sort of trend here, and actually we've taken it even a little bit further. And so this is basically revisiting this in a paper that I published earlier this year. Again, I'm using the same sort of colors to highlight things, where the main sequence systems are gray, the evolved systems are in red. And without walking through all of the things on this figure right now, it does seem to be that there's a pretty clear trend for these evolved systems, that there's like this period eccentricity trend. And we might be able to explain it by, if you assume that basically planet-planet scattering is essentially just like just depends on the age of a system. So the older you are, the more likely that there's some chaotic interaction and planets get scattered. And as they get scattered, that can pump up their eccentricities at longer periods. And that can actually reproduce the sort of features that we're seeing in the evolved population. And in fact, if things get scattered too much, they can actually get pushed into the high eccentricity migration regime and then end up as hot Jupiters around more evolved stars. If they're if they end up on 5 to 10 day periods, they can hang out there for a while. If they end up on even shorter periods, they might in-spiral basically right away. And so if we want to understand how planetary systems evolve, we really have to continue to push to these longer periods in these evolved systems, so you can say, do they continue to follow the sort of period eccentricity trend, or for when we look at the RV systems, for example, I'll just bring that plot up again. You can see that for the longer period things, we don't actually see that trend there. And so whether that's just a difference between the populations, if there's some sort of turnover or something like that, it would have to be kind of right around 1 AU period, basically. And so that's why we need to find more of these systems to figure out if there is a turnover, if those planets, exist. Basically, how stable can a planet on an Earth-like orbit be around an evolved star? We don't have the answer to that, and we're going to need to find more systems to figure that out. The other thing that we can study here, as I mentioned, is orbital decay. And so basically, you don't have to understand the axes on this plot here, but the important thing is that if you follow the arrow, that points in the direction of faster orbital decay. And so here I'm just highlighting 3 planets that I found through this test survey last year. And you'll note that one of them actually has T-ins, an in-spiral timescale that's shorter than 1 mega year. So it's potentially the most doomed planet that we've found so far, in that the planet should in-spiral into its host star in a very short time scale. Yes.
So a lot of this is based upon like their tidal dissipation assumptions, something like that. Do you have high enough SNR on some of these beta guys to get a log number based on tidal distortion?
Probably not. So basically, with the problem is that the transit depths aren't super deep. And so I think if you were to observe these systems with like JW or some sort of space-based like Hubble or something like that, then you might actually that would give you the precision to see transit asymmetries and things like that. But right now I've looked into it from the test data. I've gotten excited and then gotten unexcited about it at various moments. It's hard. But there are other things that we can do to try and constrain the tidal quality factors. And so basically, without going into the details of what these not so beautiful plots actually are saying, the point is that there are a whole bunch of different models for how the tidal quality factor, for example, for the star should evolve as the star becomes a post-main sequence system. And by studying more of these like hot Jupiter systems around evolved stars, we can actually start to test which of these models better explains the sort of orbital evolution of these evolved systems. And so, basically the thing is that for the systems that I'm looking at, we're all in that regime between 10 to the 9 and 10 to the 10 years, where things, go from, the tidal quality factors change by orders of magnitude. They're not really well constrained. But if we actually have more of these systems that are near the end of the life, we're getting toward that point where the quality factors are something like between 10 to the 4 to 10 to the 6. And so if we can actually, constrain systems where we could see orbital decay, if the tidal quality factor is 10 to the 5 or so, we can actually start to constrain these theories and test this. And thanks to TESS, we can actually do this now. And so back in last year, the first sort of combination of Kepler and TESS data was used to find this this period decay in a subgiant system. And since then, I've worked with some people in this room on putting together new test proposals to basically try and look for period decay in a wider range of systems. And as I think I put on here, yeah. So in some of these systems, thanks to the most recent TESS observations, we might have some new orbital decay detections in systems that were previously that have been known of for 10 years. And now by having like a 15-year baseline or so, we can actually constrain the tidal quality factors to that 10 to the 5 level where you're actually testing the stellar physics. And we can also do this in some systems that we actually are still TOIs, but they might have even more sort of extreme orbital decay and things like that. And so both in systems that we already knew of, but also in new TOI systems, we're going to be able to sort of look for orbital decay and test it in ways that we couldn't before. And so, yeah, new detections and constraints on orbital decay with TESS will basically change our understanding of orbital decay and stellar tides. Okay, so that's pretty much all I wanted to say about orbital dynamics. I guess I'll take a quick break right now and see if anyone else had any questions about that.
Do you have any multis?
So in our test survey, we have not found any. There is one Kepler system where there are 2 transiting planets and then a third outer non-transiting companion. And that system is really interesting because you could actually, the transiting planets are misaligned with the star, but we think that the outer non-transiting companion actually is aligned. And that so those systems are one where the planets like torque themselves out of alignment. But that's basically that's the only multi-transiting system that we know of. But we do have a lot of systems where we think we see an outer non-transiting companion, and that's in about maybe 30% of our systems. That is a good question that I don't know the answer to. I think the planets are in resonance, so probably on some level. Yeah.
I might have missed this, but for all the Eagle stars, are you assuming they originally like mean sequence of decay stars?
Yeah.
Or what? Okay.
Yeah. So basically, yeah, probably mostly F stars,
Okay.
but yeah, FGK.
Okay.
All right. Well, in that case, now I can get on to the really crazy stuff. So yeah, so the last thing I wanted to talk about was basically demographics of planet populations that you can do with these evolved systems. And I'm even gonna, it's on the slide. So you might even be able to look at potentially extragalactic populations using evolved stars. And so, okay, so yeah, if you want to find extragalactic planets, how do you do this? Well, basically you can use Gaia to identify structures that have extragalactic origins within our own galaxy. And without explaining all of the details on this plot, the important thing is that by basically using the kinematic information from Gaia, we can select basically based on the motions of stars, we can distinguish stars that are in the galactic disk or the bulge from stars that have halo basically that have, halo kinematics. And so that has how we identified the Gaia Enceladus sausage, which is shown by the blue stars on this left plot. And so this is something that I've actually spent some time thinking about since so basically what we did is to try and better understand some of these populations. Another thing that's interesting to do that you can do with these red giant stars is actually calculate ages for the stars. So again, if you can get an astroseismic signal for these stars that, unrelated to the planet stuff, so quick aside, you can actually do this astroseismology, and that gives you, again, really precise mass and radius, and that can get you an age by comparing to models. And so basically by comparing some stars that were sort of in these different populations, so the Gaia Enceladus population versus the wider halo population versus the wider disk population, we were able to basically characterize these populations and determine ages for the stars in the Gaia Enceladus survey. And what we found is that basically within the halo, Gaia Enceladus seems to potentially be not the oldest, not the youngest stars. They're kind of their own population that are kind of separate, and they don't show as large of a spread as main sequence systems. And I've continued to sort of working on this by thinking about the metal poor stars in the galactic halo. And so basically, if you can use Gaia information to compare the distribution of all stars in spatial coordinates, as I've done on the left, or again, these sort of energy versus angular momentum, these kinematic coordinates that I'm showing on the right, to say, okay, how well distributed are, in this example, the metal poor stars in our galaxy. And what we find is that basically the metal poor stars seem to trace all of the stars in our galaxy quite well, except for this Gaia Enceladus population, which is basically in this box on the right. That's why the color looks different in that box, and it's basically the same everywhere else. And so that means that the metal poor stars are probably not from Gaia Enceladus. So if we do see more metal rich stars, those are probably more likely to actually be part of Gaia Enceladus. And metal rich stars are more likely to host planets. And so that's good that if there are metal rich stars in this halo population, those are also, and we do find planets around them, those planets are also more likely to have extragalactic origins. Okay, so how do we actually find these extragalactic planets? Well, I'm not the first person to try this. Actually, there was a paper published over 10 years ago in Science where they claimed the detection, the RV detection of a planet around a star from another galaxy. I think this was part of the Helmi stream. But unfortunately, with a radial velocity detection, you really need a long baseline to be sure that the signal you're seeing is really a planet, not going to change in phase. And unfortunately, 4 years later, they got some more RVs, completely, diluted the signal, and that planet is now refuted and no longer believed to exist. And so if you want to find extragalactic planets and you want to convince people that it's a real planet, you really want to find transiting planets so that we can independently confirm that they exist. And so this is something that I've been thinking about. So basically using the sort of the same sort of Gaia kinematic information, as well as the sort of just color magnitude information to target red giant stars, we could then target them specifically in the halo. And so I worked with a student, Stephanie Yoshida, on doing this. And basically what we did, we were able to target, a bunch of these sort of the same sort of low luminosity red giant stars where we could actually, find planets in the halo. We were able to target around 1,100 of them. And unfortunately, we didn't find any transiting planets, but what we could do is an injection recovery test to see how complete our survey was to actually detecting these things. And what we found is that basically we would only be sensitive to hot Jupiters in the sample. And even there, we could only detect them about half of the time. So wasn't super surprising that we didn't find anything. But by doing this in injection recovery, we were able to place some upper limits on the planet occurrence rates for these halo stars. And basically, we're able to predict that if we were able to look at, say, 10 times as many stars with tests, for example, or with similar precision, we would be able to distinguish planet occurrence rates between this galactic versus extragalactic populations. And just thinking toward the future, basically, if we continue to look in new regimes of the galaxy, we can study larger populations of stars with potentially extragalactic origins with Roman. And so, for example, the Galactic Bulge Time Domain Survey is going to survey a whole bunch of stars in the bulge of the galaxy. There are also a lot of stars in the bulge that have been, accreted from other infalling galaxies. And so some of those might have extragalactic origins. We can also try and target things like globular clusters, where globular clusters are sometimes known to have come from extragalactic locations and things like that. So I think Roman is really going to be key to basically finding these sort of extragalactic planet populations, or at least constraining the occurrence rate of extragalactic planets. And so, yeah, that's pretty much all I had to say. In summary, planets around evolved stars are really great for testing reinflation. They're really great for understanding orbital dynamics. And TESS has really been, super fundamental for doing all of those things. And hopefully, if it continues to operate, will let us get to the next level where we can test these final sort of things that I mentioned today. And we might even be able to reveal these extragalactic planet populations, which we started doing with TESS, and I think we can take even further with new missions like Grunblatt. So yeah, thank you guys very much, and I'll take any questions you have.
So we'll let people online raise your hand first, because we've been talking and asking a lot of questions. So if you have one, raise your hand and let you unmute and go ahead. See no hands right now, so I will open up the folks here. I'd like 3 or 4 questions, but I don't want to see challenge as well.
a question on the kinematic selections.
Mhm.
Because kinematics have a really wide dispersion.
Yeah.
So there's, this always to be some kind of combination.
Yeah.
The population.
Yeah.
We would have a way of following up, you can find that. If you find something.
Yeah, so that's a good question. So I mean, you can always get spectra, and I think that would give you some indication of whether something's extragalactic or not. Again, I don't think it would be like we see this element, so we know for sure that this planet came from, Sagittarius or something like that. But in some cases, there are things like that we can look into, and so I think, for example, like certain stars that are part of at least associated with Sagittarius, while I'm talking about it, like they're known to be really low in nickel, for example. And so if we could get a high resolution spectrum of a star that, we thought to be extragalactic, and we saw that it was also had this low nickel abundance or something, that would be, one more line of evidence that it might actually be extragalactic. But I don't think we're going to have like something that says like, oh yes, this planet must be extragalactic 100% unless we actually observe it outside the galaxy or as part of like, the Sagittarius dwarf or something like that. Not necessarily. So I think like from the demographic point of view, the thing that's really nice is we know statistically what fraction of the stars in the halo should be extragalactic. And it's like 90%. It's quite high. And so for any particular system, yeah, I don't know if we have a smoking gun, but if you want to do these larger demographic surveys, this should be fine.
So I'll start with my less crazy question and go to more crazy. So you talked about kind of the damping of, look for these information, planetary informations too, around some of these, and then the rapid mass loss. How long might you have the remnants of like a disk that would disappear or something like that from the stuff that's going to escape them?
That is a really good question that I have not thought about at all. So I don't know, when material escapes, I don't think it forms a disk necessarily around planets, but I think because like, for these systems, right, you're like at an A/R star value of less than 10.
Yeah.
And so I think it's really, really hard to keep something in orbit around the planet at all. And so I think anytime that like you'd have mass loss, it would basically just escape directly into the star or directly away from the star or something like that.
Without the star?
Unfortunately, no. I think so I have not done these calculations, but other people have looked into it. And I think because like, even a Jupiter, right, is like 1/1000th of the mass. Like there are some signals that you can look for within like the first sort of like 10 to 50 years of engulfment. But beyond that, it gets really hard to tell. And there are some things that you can look for. So like there was this study that basically claimed that they had a binary system and like the chemical abundances were different in that binary system, where the refractory elements were enhanced in one of the stars, but not the other. And that was probably a sign of some sort of engulfment event. But I think in order to observe that, it either has to be really recent or a really, really massive thing that was engulfed. So I think like a brown dwarf could produce like an observable signal, or maybe a couple brown dwarfs or something like that. But a typical planet, it's quite difficult.
Oh, no, that's crazy. All right, whatever. I mean,
Go for it.
that one for lunch, but then I'll ask a crazy one now. All right, so I guess for the kind of evolution, have you looked at this in our solar system? Planet X, a red giant, what happens to it? What happens to planets that the habitable folks might be excited about?
Yeah. So I've tried to actually do this, which is like evolve a planetary system as well, and like connect that to the stellar evolution. The problem is that a lot of times for like planetary dynamics, the like interesting timescales are quite short. They're like tens of thousands of years and things like that. Whereas the stellar evolution is happening even, on the fastest points of post-main sequence evolution, it's sort of like million to 10 million year timescales. And so I haven't been able to get this to run without like crashing my laptop, basically, but I'm sure that there are ways to do it. And I've been talking to people about like smarter ways to do this in a larger population sense. And I think that would be the way to do it, is basically take, for example, like all of the Kepler, like the Kepler population, and evolve all of that forward like 5 gigayears, do you end up with a population that looks like that has this like period eccentricity relation or things like that that we've seen for these evolved systems. So yeah, that's something I'm really interested in, but so far it has been computationally untractable.
I know we talked about observing longer of a test for orbital decay, but how much more, well, if you have more test data on certain systems, yeah, how much deeper do you think you go, like smaller planet wise around? Like smaller than Neptune, say this.
Yeah, that's a good question. I would say I think the smallest we're gonna get is probably gonna be the hot Neptune system that I work with. Like, so as you pointed out, like that wasn't basically, it did not make the SNR cut of any other survey other than our own. And so there might be things as small as Neptune that are in the data. And if we have, and so for that particular target, I think we have like 6 sectors of data or something like that. And so that's something like, it's a 4-day transit. And so that's probably like 10, maybe 20 transits or so. So for small planets, I think if we had like 100 transits or something of a Neptune, like we probably would be able to see that. But it would have to be something on like a short orbit or like in the continuous viewing zone where we have tons of data. I think in terms of finding long period things, we're definitely like, it's definitely easier to find like Jupiters and Saturn. I think anything that's larger than like half a Jupiter radius will have a good chance of being able to detect. But basically, yeah, like Neptunes and smaller, I think are going to be really hard at long periods.
But I don't want the this actually, and it's far below.
It was not all static.
Yeah.
Yeah. This is
Yeah, there are also like things about like, I don't know what the target list for Plato is. I don't know if they're like taking suggestions and then once the data does get observed, I don't know if it's gonna be like public.
It's like,
Yeah,
Yeah, exactly.
when is it even supposed to come?
yeah. So, yeah. So yeah, Nicole, to answer your question maybe a little bit more, I think like if we had Kepler still, right, like that would be the ideal thing to try and find more.
All static.
Yeah, right, exactly. That would be the sort of precision that I think we'd need to find, like probably still not rocky, but like closer to rocky planets around evolved stars where you could do like
Things.
yeah, exactly. And so I think most of the sort of like, does the planet survive or not will be kind of limited to like the 10 to 30 day period range. But I mean, even there, we're seeing some pretty large differences between the planet populations. And I think that has to do with different evolutionary processes. I think that like, for example, the hot Jupiters that we're seeing around evolved systems are not the same hot Jupiters that we see around main sequence systems. That basically they are things that were maybe cold Jupiters or, coldish Jupiters around main sequence systems and now have inspiraled. And like, how many planets do they knock out of the way in that process? Like, not really clear. And so, yeah, anytime we find a transiting planet around these systems, it's like, oh, awesome, it survived. And like, and shows us that we can actually do that sort of like injection recovery tests as well to work out what the actual occurrence rates are.
I think we'll close up at least the online portion. We're gonna go grab some lunch, probably in the cafe, if anybody wants to join us, including online, if you just didn't want to get out of your office for the talk. But thank you again, Sam. Really interesting talk, a bunch of stuff with you on and crazy questions to ask.
Great, yeah. Thank you guys.